All right, so this is one of the presentations I did for a science fair back in February. It has some cool photos and stuff that we can just kind of go through.
Yes.
All right, so those are the pines. You all are familiar with the pines, giant puddle. They're very cool. So this is what I was talking about earlier with the ESCM and the 3D topography. So the white dots you see are the stomata, and the green parts are the ridges, and you can see how they are in very nice rows.
Yeah.
Okay. So this is what I did with the contact angle. So you can see on the left, that's the droplet of water. And essentially, in the beginning, I would literally take a protractor and hold it like straight up to the screen. But I'm glad I found the software that makes it so much easier to process, because like I have to go through hundreds of them and it's not fun. And on the right, because it's so difficult to capture the little ones, this is actually an image by the Keynes 3D microscope. Essentially, the warmer colors, like the red, those are what's like higher and closer to the camera lens. And the cooler colors, like the purple down there, that's like further away to show the depth.
Okay.
And then you can see the stomata, those are hydrophobic.
Yes.
And then all the ridges are hydrophilic. So this is the video process. This is the camera that I used. And how I held up the needle. This changed a little bit. I took this in the beginning.
Right.
Probably, in June-ish of my experience. Like this was a year ago because I can't go in the lab anymore. But with the blue dye, this is kind of interesting because with a humidifier, it's super, super messy. Like it goes all over the place. And then I have to stick my head in there to get the camera and get the needle. And before we figured out the safety, because then afterwards I have to wear like a mask and goggles and everything. But before that, like I spent maybe like 3 hours with my head in the fog chamber. And I came out and my face was blue, my hands were blue, and then I blew my nose, and like so much blue stuff just came out. It was really disgusting, and it was like really funny though.
Yeah.
But then the scary part was the lady in the lab bench next to me also had blue stuff come out of her nose. So we're like, ooh, this is probably some sort of safety violation.
Right.
Let's figure this out. So like I got a whole like covering thing. So now it's just like stuck in there and we're all safe.
Yes.
So yeah, next slide. This is some of the photos I've taken. And you can see it kind of grows over time on the ridges. And yeah, these photos are very pretty. I like them. Oh, yeah, I didn't mention this before, but I kind of did some type of image processing method to kind of characterize exactly when and where the water goes in a mathematical way.
Oh, okay.
And yeah, that's more about the image processing. I probably won't get into that. And yeah, those are the results that I mentioned before, where it starts, accumulates on the ridge, goes over to the valleys.
Right.
And then this is part 2, the biomimicry part. So these are the transparencies. And I don't know if you can see like the little lines on them, but those are the hydrophobic toner lines that I put. And on the right side, that's the control. That's a homogeneous hydrophilic surface, plain transparency. On the left side, that's the micro pattern. And you can see how much faster the water's going down. It's not just stuck there on the surface, which makes the whole process so much faster. This is the science-y physics part. I can talk about that a little bit. So essentially, a critical roll-off angle is if you put a droplet on a piece of paper and you tilt the paper, when does the droplet roll? And you can measure transportation speed and efficiency by seeing what surface has a smaller critical roll-off angle. So that's essentially what I was doing. There's a machine that is specialized in doing that, which is really convenient. It already has like the protractor and camera and everything all set. So the process for this was a lot easier. Essentially, the critical roll-off angle of the micro pattern was just significantly smaller than the critical roll-off angle of the homogeneous surface, which adds to the idea that the transportation rate is a lot faster on the micro pattern than it is on the homogeneous surface.
Mm-hmm.
This is one of the equations that I came across that kind of describes why. Basic gist of it is that when you decrease the width, which is what you're doing when you have those constraining lines, you decrease the width without affecting the volume. That essentially just takes away from the pulling force. Sorry, the force that's like keeping it on.
Okay.
And then device prototyping.
Yay.
That's the CAD design, that's the Lego version. Brought these to the state park. One of the big findings I had was that this like vertical thing, it just doesn't work. Like I put it overnight and there'd be nothing on it. That's because like fog kind of like lands. It needs something to land on.
Right.
If it's vertical and it's on the ground, it's kind of useless.
Right.
So I have to angle my device a bit. So yeah, here I am testing out the plate orientation. A flatter surface corresponds with more water collected. Oops. And then, yep, did it with more panels, same results. More devices / prototypes. And then, yeah. So this was in February, so I've done more. Oh, okay, yeah, this is kind of cute. So Torrey Pines Docent Society, they found me at the science fair in 8th grade. And so every year they invite me to speak at their meeting. And then they give me a parking pass to Torrey Pines every year. And then last year they made me this really cool cake. I love this cake. Amazing. And there's me at the extension reserve late at night dropping off my samples. So yeah. Here it is. Looks a lot like a pine needle. And this is probably the 6th or 7th prototype I've made, and there's still a lot further to go. It's gone through all sorts of variations, but this one is really inspired by the needle structure itself, as you can tell. And the distance between the holes, I don't know if you can see, it's kind of calculated so that it maximizes the surface area of the needle and it also enables airflow to go through. So yeah, this is my prototype. This is a 3D print. This gray thing is 3D printed, and it's going to be tested a lot more in the future. Yeah, so that was kind of my most recent development, and in addition to the micro pattern, which hopefully the micro pattern, I don't know if you caught it in the video, but the alternating hydrophilic and hydrophobic micro pattern, that should be printed on these, but I still need to figure out how.
Would you mind sharing a little bit of how your prototype works? It looks very interesting.
Yeah, sure. So the intention behind this prototype is after it, so this is coated in the micro pattern, and the stripes are supposed to be made in a way that facilitates it rolling down the straws. And then these holes, their diameter is like a little bit larger than the straws, so it should go inside this secondary bowl. And there's this outer covering just because there's so much dirt and stuff. It's just supposed to protect the water that gets harvested, and then it will all end up in this bowl down here. Is how it's supposed to work.
Okay, I see. That's very interesting. Do you guys have any questions for her?
Question.
Yeah.
How do you measure its like performance?
Keep it pretty simple, just grams.
Okay. Like does it depend on like the outside conditions or anything like that?
It totally does. Yeah, that's why most of my testing has to be done in the wintertime, because in the summertime there's just no fog, or I have to do it in the fog chamber. In the fog chamber, it's more like milligrams per hour, because I just can't keep my humidifier running overnight.
I see.
Okay.
Where do you see like this kind of prototype going into the future? Like, what kind of difference can it make?
Yeah, that's a great question. So I hope to develop a device that's able to be mass manufactured for areas that have fog but are in drought. And there are quite a few moisture harvesting technologies that are, being developed right now. But one of the biggest differences between this and the other ones is that it's completely passive. It doesn't require any energy, and in doing that, it's a different audience it's targeting. So like MIT, they have a research group that makes metal organic frameworks. So like a really porous, expensive material, as well as like solar powered in order to heat up the air and cool it down. And then there's a company in Arizona called Zero Mass Water, and they develop source panels, which is like $2,000 whole like home system. Like it's Arizona, it's super dry, so we'll take it and then it goes right into your refrigerator dispenser. Uh, both of those are really expensive and they require a ton of energy, even if it's solar energy, but they work in low humidity conditions. Mm-hmm. This one is more so targeted for like Chile and Peru, where there's so much fog, and but energy might be a little bit more difficult, and the price is also considered.
All right, I see.
How does your prototype absorb the fog?
Yeah, that's a good question. So, I wouldn't say it absorbs the fog, but more so how does it land in such a way that it will stay? And so that has more to do with the alternating hydrophilic and hydrophobic micropattern. So if you can imagine just a bunch of stripes like on a sheet of paper, half the stripes are hydrophilic and half the stripes are hydrophobic. And the hydrophilic, it likes the water. It will attract it. So like a piece of paper, if you put a water droplet on it, what happens? It spreads out. It likes the paper. So the water lands on the hydrophilic stripes, and then more and more collect on the hydrophilic. But then as it expands, it can't, because there's hydrophobic right next to it. It's being squeezed. And because it can't go outwards, it goes down. So that's how the water kind of falls off. And that's really important, because the more quickly that the water falls down, the more water can condense. So that kind of just speeds up the entire process.
So do you coat the inside of your straw so that with the hydrophobic material, so the water, once it absorbs it, it would go down right away, or instead of sticking to the wall and get evaporated?
So are you asking for in general, or like?
Generally, in the inside the straw, so because once your moisture get landed inside the straw, will it go down, okay, or will it just stay there and eventually get evaporated? So you will not be able to collect it.
Yeah, that's a good question. So it's not intended to go inside the straw, but it's intended to roll down the straw as quickly as possible so that it can get under this covering. So even if it does evaporate, it will just get stuck to the ceiling of this covering. It will inevitably, in that process, while it's rolling down the straw, lose some to evaporation. But that's kind of the reasoning behind why I like to call it the transportation rate, needs to be high, and why there has to be the hydrophobic stripes. And yeah, that's why I don't have like a completely hydrophilic surface, because then it'll get on, but like you said, it will evaporate because it can't get off and into the bowl.
So have you tried and see whether you give it a fixed amount of the moisture there, how much it actually collected?
Yeah, I most of my like solid testing with good data and good numbers hasn't been on the prototype, but it's been on just the micropatterns with the transparency, like I mentioned in the video. And with that one, I optimized the ratio of hydrophilic and hydrophobic, and the best ratio collected 2.6 times more moisture than just a plain hydrophilic surface. And in that one, it like the micropatterns are like teeny tiny, like probably this big. And in 1 hour, it collected probably 0.1 grams, which if you scale that up, that's a pretty good quantity for size and also time.
Mm-hmm. All right, thanks.
Yeah, no problem.
So I will briefly tie this into our drought into fog. So let me share screen. There we go. Okay, so today is day 4. Today let's recap a little bit about the past few days. So today on Monday, we had talked about, what the Torrey pine trees are, who are they, how do they get their name, and what makes them so unique. One of its uniquenesses, I guess we could say, is that it can water itself because it's able to collect fog. However, because we're in a state of climate change, because we're releasing too much carbon dioxide, one effect is climate change, as we can see here. Because of climate change, we have a temperature increase, kind of creating the greenhouse effect. Because we're having warmer temperatures, we're in a drought. And because we're in a drought, first, there's a lack of water, and our Torrey pine trees aren't able to produce sap to push out our bark beetle friends. Although, our bark beetles they depend on the Torrey pine trees to live. However, because of drought, the Torrey pine trees can't produce sap to push out our bark beetles. So that's one problem caused by drought. Today, the second problem that we learned caused by drought or warmer temperatures is that there's not a lot of fog. So, and fog is important because Torrey pine trees kind of depend on the fog to get the water they need in order to survive. So, because the Torrey pine trees don't have enough water, they're slowly starting to die because they don't have enough fog. So with that said, Emily is trying to create a prototype that would enable humid places to collect fog and hopefully help places that are in a drought collect enough water. So that's it for today. Just wanted to remind you guys that we will be meeting at 3 tomorrow, and I Love a Clean San Diego will be sharing things and ways we can help slow down climate change. Stop sharing. Okay. Do we have any more questions? Going once. Going twice. None that I see. Alrighty. Thank you all for being here, and I hope to see you guys tomorrow.